Hello everyone, I'm Zhou from the University of Rochester. Today I'm going to present our work Silhouette, efficient protected shadow stacks for embedded systems. Nowadays, microcontroller-based systems are almost everywhere. The engine control unit of a car, the Bluetooth module of a smartphone, the Wi-Fi module of a smart light bulb. Security is an important issue for these small devices because they are often integrated into a large complex system. And if these small components are compromised, the whole system could be compromised, such as being hijacked. Those embedded devices usually have a very limited CPU speed, limited memory, real-time constraints, and the software running on them have frequent direct operations on hardware. With all these conditions, C is the primary choice to write programs for these devices. We all know C is not memory safe. Among all the memory safety problems, control flow hijacking is one of the most serious ones. By corrupting control data, an attacker can divert the control flow of a program to selected destinations. To mitigate the control flow hijacking attacks, control flow integrity is a promising direction. It can restrict where the control flow of a program can go. However, fine-grained control flow integrity policies are usually very expensive, while practical CFI policies are usually cost-grained. Many recent work show that cost-grained CFI policies are not very effective. One common weakness is that a return instruction is often allowed to return to multiple places. For example, a return is allowed to return to any instruction that follows a core instruction, although at runtime there is only one legal destination. Most of the attacks demonstrated in those breaking CFI papers exploited this weakness. So in this work, we present Silhouette, a compiler-based defense that guarantees the integrity of return addresses and also provides coarse-grained forward edge control flow integrity. It only incurs very low performance and code size overhead. We developed for the ARM v7m architecture due to its popularity, but our technique can also apply to many other ARM embedded processors. Next, I will talk about the design of Silhouette and evaluation, and I will summarize. First, I need to talk a little bit about the shadow stack. Shadow stack is a common technique to protect the return addresses efficiently. Essentially, by storing the return addresses to a separate dedicated memory region called a shadow stack, even if the return addresses on the regular stack are corrupted, a function can still return to its correct caller by directly using the return address from the shadow stack. But an obvious problem is the shadow stack itself also needs protection. For a shadow stack protected program, all store instructions can be categorized into two types. One type of stores are those that are supposed to update the shadow stack, and the other type are all other store instructions. From a shadow stack's point of view, the left can of store instructions are legal, and the right can are illegal. So to protect a shadow stack, a natural question to ask is, can we make the shadow stack writable only by its legal stores? To answer this question, I need to first give some background information on ARM v7m. There are two execution modes, privileged and unprivileged. This is similar to the kernel mode and the user mode of a general-purpose computing system. But unlike a general-purpose system, embedded systems usually run everything in privileged mode by default to avoid the expensive overhead of switching between the two execution modes. Second, memory access permissions are usually configurable. For example, we can configure the shadow stack region to be writable only by privileged stores. So if a program runs in unprivileged mode, a normal store instruction would not have write access to this region. Now, with this background information, we can ask a second question. Is it possible to make only the shadow stack legal stores privileged and all other stores unprivileged? Because if so, then all the illegal store instructions would not have a write access to the shadow stack region, and that is guaranteed by hardware. The answer to this question is yes. There is one special store instruction called unprivileged store. An unprivileged store instruction acts as if it is running in unprivileged mode when it is actually running in privileged mode. For example, this is an unprivileged store running in privileged mode. If we have configured the memory address as 0+12 to be writable by privileged stores only, then this instruction would fail. Here is how Silhouette uses unprivileged store and memory configuration to protect the shadow stacks. It configures the memory region for shadow stack to be writable only by privileged stores, and it transformed all stores to unprivileged ones, except those shadow stack legal stores and those that are required to run as privileged. The overall effect is that even if memory is corrupted and the control flow is hijacked, illegal store instructions would not have right access to corrupt the shadow stack. And we call this technique store hardening. Store hardening comes at a price. There are many different normal store instructions, but there are only 3 different kinds of unprivileged stores. So in order to transform most normal store instructions to the 3 unprivileged ones, sometimes we need to add extra instructions. Let's take a look at 2 examples. In the first example, a normal store instruction can be transformed to an unprivileged one directly. However, in the second example, we need to add a pair of arithmetic operations to do the transformation because unprivileged stores don't support negative immediate operands. So the first case doesn't incur any performance or code size overhead, while the second case does. Remember I mentioned earlier that besides those shadow stack legal stores, there are also some other store instructions that must run as privileged. So we must ensure that those store instructions cannot be exploited to corrupt the shadow stack. So Silhouette also handles forward edge control flows. It adopts label-based forward edge CFI for indirect function calls, and it also handles indirect jumps, such as large switch statements and computed gotos. To summarize the design of Silhouette, after the LVM machine IR code generation, Silhouette first transformed a program to use a shadow stack for return addresses. It then applies the store hardening path to transform all the shadow stack illegal stores to unprivileged ones. And finally, it runs a CFI path for forward edge control flows. The security guarantee is that any return instruction will always return to its dynamic legal destination, and the forward edge control flows are also restricted. If you are wondering if there are any corner cases that could break the security guarantee of Silhouette, please have a look at the security analysis section of our paper. Now we have seen the design of Silhouette. Let's see how it performs. We evaluated both the performance and the code size overhead of Silhouette on a Cortex M4 processor with the CoreMark-Pro and the BEEBS benchmarks. CoreMark-Pro is an industrial standard benchmark suite for embedded processors, and BEEBS covers a wider range of programs. We measured the impact brought by all the 3 major components of Silhouette, as well as Silhouette as a whole. On CoreMark-Pro, only one program's performance overhead is over 2%, and the average performance overhead is only 1.3%. The red bar and the green bars on this graph shows that for most programs, most of the performance overhead comes from the store hardening path. For code size, Silhouette incurs 8.9% overhead. And for most programs, most of the code size overhead also comes from the store hardening path. This is simply because store hardening path adds a lot of extra instructions, while the shadow stack and the CFI path don't. On BEEBS, we run 29 programs in total, but here, due to space limitation, we only show programs whose performance overhead are over 5%. Overall, most programs slow down less than 5%, and the average performance overhead is 3.4%. BubbleSort has the highest performance overhead because its major computation is in a small loop, and the store hardening path adds extra instructions for stores in that loop. And for code size, Silhouette only incurs 2.3% overhead on average. The fact that for most programs, most of the performance and the code size overhead comes from the store hardening path made us wonder, is it possible to configure the shadow stack region to be writable only by unprivileged stores, but not by privileged stores? Because if so, we can simply configure the shadow stack to be unprivileged write-only and transform only shadow stack legal stores to be unprivileged while leave all other stores unchanged. We call this design Silhouette-Invert. Unfortunately, currently this configuration is not supported by v7m, so we proposed 2 solutions with minor hardware changes. Due to lack of time, please see the paper for details. The simulated results show that on CoreMark-Pro, Silhouette-Invert only incurs 0.3% performance overhead on average, And for each benchmark program, Silhouette-Invert performs better than Silhouette. On BEEBS, Silhouette-Invert incurs 1.9% performance overhead on average, and there is only one program for which Silhouette-Invert's performance overhead is a little higher than Silhouette's. And this is simply because Silhouette-Invert transforms those shadow stack updating stores, and this program has many function calls. If you are curious why this Livingston program's performance overhead is still nearly 20% on Silhouette-Invert, please check out our paper or talk to us after the talk. To summarize, in this work, we developed a Silhouette, an efficient defense to protect the return addresses for ARM embedded systems. It incurs very low performance and code size overhead, and we also proposed a variant of Silhouette called Silhouette-Invert. It further decreases performance and code size penalties with minor hardware changes, and we open sourced our code. Thanks very much for watching the video. Now I'm happy to take your questions.